Please enjoy the video. What are vectors? This is a vector. A vector has magnitude and direction. 1. Translation of a plane. If you translate the graph y equals axz plus bx through a distance c in the y directions, its new equation is y is ax squared plus bx plus c. In general, if you translate the graph y equals function of x, a, distance c, units in the y direction, its equation becomes y is function of x plus c. The essential feature of a translation is that the sheet moves over the grid without turning. A general translation would move the sheet k units across and l units up the grid. This is shown in figure 6.1.1, where several points move in the same direction through the same distance. Such a translation is called a vector and is written k and l. Number 2. Vector algebra. It is often convenient to use a single letter to stand for a vector. In print, bold type is used to distinguish vectors from numbers. For example, in P is vectors k and l, where P is a vector, but k and l are numbers, called the components of the vector P in the x and y directions. Then I'm going to represent the difference between vectors and scalar. Now I'm going to use a generic vector P, but that could be anything. We're going to use the same notation all the way through. So if I have a vector P, you're often going to see it in textbook as a bold font, and that bold font represents the fact that is a vector. If that same P was just a scalar, it would be printed out in a normal font. Now, sometimes it's hard to tell a difference between a normal font and a bold font. So we need something a little bit clearer sometimes. And so if you've got a vector, you're going to want to have that arrow on top. So if you have one quantity that is written with an arrow on the top, you know that quantity is a vector. If you want to make sure that it's absolutely clear that you're talking just about the how much, we can use the absolute value sign. So when you see the arrow on top, you know it's a vector. If you see the absolute value sign, you know it's a scalar. For example, in P is vectors k and l. Look at figure 6.2.1 show that as P equals sk and sl, we have s as a scalar, and s is minus 1. In particular, minus 1 multiplied by P is vectors minus k and minus l, which is a translation of the same magnitude as P but in the opposite direction. It is denoted by negative P. Operation on vectors. In figure 6.2.2, P and Q are two vectors. To form their sum, you want to represent them as a pair of arrows by which you can trace the path of a particular point of the moving sheet. In figure 6.2.3, P is shown by an arrow from U to V, and Q by an arrow from V to W. Then when the translations are combined, the point of the sheet which was originally at U would move first to V and then to W. So the sum P plus Q is represented by an arrow from U to W. Addition of vectors satisfies two important properties. 1. The commutative law, which states the order of addition doesn't matter. A plus B equals B plus A. Number 2. The associative law, which states that the sum of three vectors does not depend on which pair of vectors is added first. In the brackets, A plus B plus C equals A plus in the brackets B plus C. Vector subtraction. We define subtraction as addition with the opposite of a vector. B minus A equals B plus in the brackets negative A. Scalar multiplication. Scalar multiplication satisfies many of the same properties as the usual multiplication. Number 1, S multiplied by in the brackets A plus B is SA plus SB. Number 2, in the brackets S plus T multiplied by A is SA plus TA. Number 3, 1 times A is A. Number 4, negative 1 times A is negative A. Number 5, 0 multiplied by A is 0. 3. Basic unit vectors. If you apply the rules of vector algebra to a vector in column form, you can see that P is vectors KL is vectors K plus 0 and 0 plus L equals vectors K and 0 plus vectors 0 and L equals K times vectors 1 and 0 plus L times vectors 0 and 1. The vectors 1 and 0 and 0 and 1, which appear in this last expression, are called basic unit vectors in the x and y directions. They are denoted by the letters I and j. So, P is Ki plus Lj. This is illustrated by figure 6.3.1. The equation shows that any vector in the plane can be constructed as the sum of multiples of the two basic vectors I and j. Example: express each of the following vectors as column vectors and illustrate your answer geometrically. A equals I plus 2j. B equals 4i negative 3j. Okay, let's say P is AB, where A represents the x-axis and B represents the y-axis. And in unit vector, vector P is A vector I plus B vector j. In the question, we know I plus 2j, where 1 is A and 2 is B, because vector I is paired with x and vector j pairs with y. Then the column vectors from are vectors x and 2y. To illustrate vectors, the first step is to create an x-axis and y-axis. X is at point 1 and y-axis is at point 2. Then a vector line is drawn from the center point to the point A. Okay, next question. B is 4i minus 3j, and it is known that the value of A is 4 and B is negative 3. Then the column vector found is a vector for x and negative 3y. To illustrate the vectors, the x-axis and y-axis are created, where the x-axis is at 4 and the y-axis is at negative 3. Then a vector line is drawn from the center point to the point B.